This hour we continue with our first lecture on the range and capacity of wired and wireless link to find out what do we actually need from our communication electronics. The previous hour the previous hour we looked at the Shannon theorem. Here I corrected for signal energy, so each signal is each cloud here, and we also have signal period here. We observed, we looked at the information that we can transfer with our signals, and we look at the capacity, so the amount of information we can transfer per unit time. We looked at the different limitations like the natural noise. Electronics is close to this noise. We looked at the various limitations. We may have the power limited, or we may have the bandwidth limited link. This is both we in practice we encounter both limitations, and we looked at a very simple example of a telephone modem where we don't actually look at the attenuation of the line, we don't look at the line, we look just at the bandwidth and the signal to noise ratio that's available and what can we get out of this bandwidth. So this hour we have to look at the different links, how they are made in practice. And one of the first links was a wired link. A wired link, all wire links behave, copper wire or metal wire links behave in a similar way. The most common solution is a coaxial cable link. The equivalent circuit of a coaxial cable includes a series and any two-wire link, maybe a twisted pair here besides coaxial cable, maybe other metal line here, maybe shielded twisted pair. Any such electrical connection has a series inductivity and a parallel capacitance, serial inductors, and has losses. Usually with losses, the most important source of losses is the resistance of the wire. Metal wires have a finite resistance. They are not made of superconductors. There may be some loss in the capacitor, in the dielectric of the capacitor, here. But this loss in this dielectric, usually capacitors can be made very good. We have very good dielectrics and we have very small losses in the capacitors. So in our first discussion today, we can simply neglect the losses in the capacitors. We only consider the losses in the wire making up the inductors. The equivalent circuit of a transmission line has distributed inductivity of the inductors, distributed capacitance of the line, and an equivalent circuit should contain many such sections where we have both inductors, capacitors, and resistors for the losses inside the inductors. The more such sections do we model, the better is our approximation to a real distributed capacitor, distributed resistor, distributed inductor equivalent circuit. Any such line has a characteristic impedance. If losses are low, so if this resistor is low and we are trying to make low loss lines to have low attenuation, the characteristic impedance is the square root of the inductance per unit length and capacitance per unit length of the transmission line. The ratio of the two, square root of this. And the characteristic impedance has units of ohms. In theory, this characteristic impedance is a complex number if we consider also the resistance. But this resistance is small. So to the accuracy of our measurement, the measurement we can make this characteristic impedance is practically a real number, and its value is expressed in ohms. To get the best possible transmission over such a line, it makes sense to have both the transmitter and the receiver matched to this characteristic impedance. So we don't have any reflected waves here on this line. We don't have any multi-path distortion on this line. We have the maximum power transfer on this line. Resistors, of course, cause losses. And the attenuation coefficient alpha is resistance per unit length divided by twice the characteristic impedance of such a line. The attenuation coefficient, since this is a mathematical derivation, it's given in exponential functions or natural logarithms in the other way. So exponential functions, so e is this 2.718 and so on, the basis of the natural logarithm, and the unit is here neppers per meter. Neppers are defined on the voltage. On the voltage we have on the line. So the voltage of the transmitter is the voltage of the receiver is the voltage of the transmitter times this decaying exponential function of the attenuation coefficients and distance we cover. Power, of course, goes with the square of the voltage. Since this voltage is given on the characteristic impedance, both transmitter and receiver should be matched of the characteristic impedance, and power goes with the square, so power 2 here, and the attenuation per unit length of this line is usually given in decibels per meter. Now converting neppers per meter to decibels per meter is this factor here, this factor 20 divided natural logarithm of 10. 10 would be for decibels, 2 is for this square here, and natural logarithm of 10 to convert natural logarithm to decimal logarithm. This is usually the figure given for coaxial cables in decibels per meter. The attenuation of power, since we have a match situation. So if we look at a long distance communication, a coaxial cable, say of half an inch diameter, will have at 100 megahertz bandwidth, will have an attenuation of minus 20 dB per kilometer. Usually attenuation, we write it with the minus sign here. Attenuation coefficient, we write it with the plus sign. So be careful a little bit here about signs. Attenuation always means that we receive less power that we transmitted. But the way these symbols are used, attenuation coefficient is usually given as positive. Attenuation per length is usually given as minus decibels per meter, so minus 20 dB per kilometer for a typical half an inch diameter, outer diameter coaxial cable. So with such a coaxial cable, if we do communication with a bandwidth of 100 megahertz, we need amplification or regeneration of the signal about every minus 40 dB of attenuation. 40 dB of attenuation, we get it at a distance of 2 kilometers. So every 2 kilometers, we have an amplifier. We need an amplifier or a regenerator. This may be okay for short distance communication, but for long distance communication, the number of amplifiers or regenerators becomes very, very large here. In order to overcome the problem of coaxial cable link, or maybe another transmission line made of metals, the most important solution is to eliminate the metal. Make waveguides that contain no metal, because we are able to make good dielectrics. And our next communication medium is the optical fiber. Where is the idea behind the optical fiber? Okay, we need a special light transmitter, and I shall look about that in the discussion on electronics. We need a laser diode to produce light, modulated light, and we need a photodiode on the other end of the link. So this is not a direct electrical communication. We need to convert an electrical signal to light and light back to an electrical signal. But the bare transmission line we have in between, it's made only of dielectrics, and silica glass may be a very good dielectric. We can make very clean silica glass for semiconductors. That's a requirement for MOS transistors, metal oxide semiconductor transistors. That's a requirement for MOSFETs, that we have very clean silicon oxide. And this silica glass can also be used using the same basic chemicals to make optical fibers. How do we obtain how do we guide the radiation over such a device? We guide the radiation by using two different refraction indices. A lower reflection index N2 in the cladding, and a higher refraction index N1 in the core. In this, if we carefully select the angle of the ray propagating through such a structure, we can obtain a total reflection on each of these transition core to cladding, so N1 to N2. If the angle is shallow enough here, we obtain a total reflection. A total reflection means gamma, reflection coefficient, the magnitude of gamma mathematically equal to 1. So there is no loss occurring in these reflections. But we should take care that the cladding is thick enough. The cladding should be much thicker than the wavelength. So since we have here an exponentially decaying field in the cladding, so that field decays before it reaches some lossy component here. The size of the core is another variable we have here, the core size, and the core size may span from 3 micrometers to 60 micrometers for conventional near-infrared light communications. This device first was thought useless in 1960. The attenuation was 1000 dB per kilometer, 1 dB per meter. So this was useless for long distance communication. There were optical fibers for some short distance experiment for galvanic separation of two electrical devices, so you don't have like high voltage and so on. But this was useless. With the advance of semiconductors, the advance of technology of producing very clean silicon, very clean silicon oxide for MOS transistors, yielded already in 1970 an attenuation of minus 17 dB per kilometer. This is actually competitive to coaxial cable. The attenuation is similar to coaxial cable built by the Corning Glass company, and this is the actually the point where optical fiber becomes competitive with coaxial cable. Not just compatible, but shortly after that, much better than coaxial cable. Much better. This is almost the theoretical limit for silica glass at a wavelength that's near visible, near infrared wavelength of 1.52 micrometers in free space. Not in glass, because glass has a refraction coefficient larger than 1. There are other materials like thallium chloride that has a theoretically even much lower attenuation than we should have a minus sign here. Much lower minus sign is missing here. Attenuation than silica glass, but in practice the losses are 1 million times higher. At a wavelength of 3 micrometers, this is not useful. This thallium chloride is not useful at 1.5 micrometers, but at 3 micrometers. The external diameter of this device spans from 250 micrometers to 80 micrometers, but the standardized value nowadays is 125 micrometers, plus minus half a micrometer or even less, otherwise we cannot splice these fibers together. Fibers can also be made for very clean plastic, but the attenuation is much larger. Minus 150 dB per kilometer is useless for long distance communication, but this plastic fiber is much more useful for other applications here. So it has its own application range, but not long distance communication, what we are interested in. How does this attenuation behave? The attenuation here is plotted as a function of wavelength, free space wavelength, or as a function of frequency. If we are talking about light, visible light is 400 terahertz, is 750 nanometers. That is close to red light. Near infrared range, where this attenuation is the lowest. Here also the minus sign is missing. The minus sign is missing because we simply write simple things here. And we see that glass has some natural limitations, has electron resonances in the UV region, ultraviolet region, has infrared molecular resonances, and these two define a minimum attenuation at about 1.5 micrometers, the lowest attenuation. But glass is really glass is really an amorphous substance. It's not a crystal. So molecules are not arranged in any order, and we have Rayleigh scattering on these randomly positioned molecules, and this Rayleigh scattering that increases with the fourth power of the frequency is a significant contribution. So actually we have the minimum attenuation here at 1.55 micrometers. When we reach this magic value of 0.2 dB per kilometer, minus is missing here, to simplify this drawing here. Of course, optical communication did not start here. Optical communication actually started at 850 nanometers due to the limitations of the electronics. First lasers and first photodiodes only operated at 850 nanometers. Photodiodes made of silicon and lasers made of gallium arsenide. As technology advanced, optical communication shifted to longer wavelengths, because at 1300 nanometers, available germanium photodiodes could be used, but lasers had to use compound semiconductors, so indium gallium arsenide phosphide lasers. This is not yet optimum regarding the attenuation, but it's optimum regarding some other issues, especially chromatic dispersion is lowest here. And finally, communications moved to the third window, around 1550 nanometers. Well, again we have compound semiconductors, both for the laser and for the photodiode. Germanium can be used here, but is not very sensitive, so germanium does not have very good performance here. So we have to have compound semiconductors. This is only around the year 2000 that communications moved here. So this is 1980, year 1990, year 2000 that optical communications made it here. With the minus sign on the attenuation, of course. So optical communications is nowadays used for long distance communication over cable, and since the prices of the hardware is going down, also for short range communications, also for computer networks, also for Ethernet. So the very cheap components are already here, but they are still more expensive than copper wire. The real problem is here this diameter of the core. Even 60 micrometers is small, and this is difficult for splicing. At lower dimensions, it's even more difficult to splice fibers. So fibers actually The good fibers, the single mode fibers, actually require a core of 9 micrometers, and 9 micrometers in between here, it's very difficult to splice. And that's the main reason of the cost. Not just to splice, also to couple to the laser, to the couple to the photodiode. And this is the reason of the high price of optical communication. Otherwise, optical fiber is extremely cheap to manufacture. It's the far cheapest type of cable we can make. On the other hand, we have, so these were wired communications. Well, wire may not be just made of metal. I think wired should be really named. Also, optical fibers here are treated as wires. In fact, we are also always talking about guided waves. Guided waves in a coaxial cable, guided waves in an optical fiber. So, if we do not want to rely on guiding, if we want to overcome free space, where we have no material to guide our waves, then we have to deal with wave propagation. Wave propagation to make a wireless link, because the free space is not going to cooperate. Hopefully the free space is not going to attenuate our signal, but at least it's not cooperating in our link. So in a wireless link, we assume that the transmitter transmits waves in a solid angle omega. We cannot make a collimated beam for long distances. Every collimated beam at some point it's going to open up in a solid angle omega. If we have no losses in the free space, so we have a lossless free space, like vacuum is a lossless space. Also, the Earth atmosphere is quite transparent at some frequencies, like radio frequencies, like visible light is quite transparent. This beam at the range R expands to a surface that's omega solid angles times r squared. And the receiver probably has a smaller area than is this A here. The beam expanded to this area. The receiver has a smaller area. It can only correct power from this area. So here we really have the ratio between, here we have the whole power we have over this area that the beam expanded, and we can only collect this power here. So the beam, our propagation loss is simply the ratio of the two areas. We have the power density is the transmit power divided by this area, and the received power is the power density multiplied by the surface of our receiver. Of course, having everything everything oriented correctly, so to get the maximum power into the receiver. What we see from our equation is here that the received power decays as inversely proportional to the square of the distance. This is a very slow decay when compared to what we have with transmission lines. With transmission lines, we have, where we had guided radiation, we always have attenuation. Attenuation had an exponential function here, or with decibels, it's a logarithm with the base of 10. But still, the exponent function of 10 to the some exponent. Here we have e to sine, so we have some exponential decay of the received power. In free space communication, the received power is not proportional to the does not have an exponential decay. It only has a decay that's inversely proportional to the square of the distance. So r to the minus 2 here. If we had losses here, we also would have an exponential term here. But we try to use wireless links on frequencies where this space can almost be treated as lossless. if we have some optical loss, then there are many different formulas to treat optical loss. Usually the diffraction is the mechanism to still transfer some power from the transmitter to the receiver if we have a obstacle in between. On the edges of this obstacle we have diffraction, wave diffraction. And the power in the receiver, we receive in the receiver, is inversely proportional to some higher power of the distance. So minus n here, where this n is between, for most communications, between 3 and 5. Of course, this alpha here should also contain units. So power of the transmitter and something to compensate for this meters to the minus 2 or meters to the minus n here. This is the more complicated case. It's still used somewhere, like mobile communications always cannot always count on free space propagation. Wireless communications always has usually it's calculated, wireless communications are calculated to use this obstacle loss. Obstacles are not that bad. They certainly obstacles increase loss, but they may increase the number of modes we can use in a wireless link, thus increasing the spectrum efficiency. So obstacles are not always that bad as written here. Talking about radio links, we should also know that this discussion here, we had on this picture here, this discussion is only valid at very large distances. It's only valid at very large distances, where we have the so-called Farfield. This is also called the Fraunhofer region. Farfield, where we can also talk with wave optics. We have other regions closer to our transmitter. Our transmitter is this big yellow circle here. Closer regions that have a different behavior than the far field. The formula in the previous slide here, the problem is only valid. This is only valid in the far field. So a condition is that we have the far field here. If we look what we have here, in the close proximity of our transmitter, we have the reactive near field. Reactive near field, most of the field here is concentrated in stored energy in this frequency. This energy does not flow anywhere. This energy just oscillates around our source of radiation, and that's the reason why it's called reactive. So reactive like capacitors and inductors. We have a region in between which is called the radiative near field. In this radiative near field we have geometrical optics. This is also called the Fresnel region. Interestingly, we use all three. We use the far field, we use the radiative near field, and we use the reactive near field in our communication. Of course, reactive near field will be used in short distance communication. In fact, if we look 150 years ago with the first radio experiments, 140 years ago, 130 years ago, made by Heinrich Hertz, Heinrich Hertz tried to prove the far field phenomena here, but other people experimented at much lower frequencies, like the many early radio experiments, like Nikola Tesla, like Guglielmo Marconi, and they didn't know that, but they used a much lower frequency. That's the reason why the lambda here, the wavelength, was much higher. And all their experiments the first experiment took place in the reactive near field, where conditions are much different. In the far field, we have the ratio between the electrical and magnetic field is exactly equal to the free space impedance. So this is a square root of the ratio of magnetic permeability and the electric permittivity of the space. And this is close to 377 ohm. In the reactive near field, there is no relationship between the electric and magnetic field. We may have so-called electric antennas which produce high electric field here. We have magnetic antennas like loops that produce a high magnetic field in the close proximity of the antenna. The short range of this reactive near field is sometimes useful if we want to have communications with a well-defined radio range. One such communications is are the bank cards, the wireless bank cards that we used to get the money or make payments with them. We actually have to approach this bank card to the machine to be able to establish communication. And here is where the reactive near field is very good. A thief that would like to steal our money cannot create this strong near field at any practical distance. So the bank card only works over a distance of perhaps 10 centimeters. It is completely deaf at 1 meter distance because of this reactive near field decaying so quickly with the distance. So this is useful. The least understood part of the range of a wireless communication is this Fresnel radiative near field. Maybe it's best understood in geometrical optics. In geometric optics, with some lenses, we can transfer one image from one place to another place and still having a real image on some screen using lenses. And this is what Fresnel radiative near field does. So where is now the comparison between these three regions? In the far field, we only have two modes of propagations corresponding to the two polarizations. Here the spectrum efficiency is lower than 20 bits. As we approach the Fresnel radiative near field, in the Fresnel near field we may have multi-mode transmission, and the spectrum efficiency may be much larger than 20 bit. In practice, each mode of communication here corresponds to 1 pixel on the image, and we can have pictures, we can transfer pictures here with many thousand or many millions pixels. So these things, this spectrum efficiency goes here to tens of millions of bits if we transfer 1 million pixels, but at very short range. At the boundary between this Fraunhofer field and Fraunhofer region and Fresnel region, we have what we call today MIMO. MIMO is also multi-mode transmission, but limited to more than 2 modes, but still a low number of modes. So here we may achieve spectral efficiency around 20 bits, and this is where MIMO comes. Of course, massive MIMO is trying to move into the radiative near field further close to transmitter to have more modes available. The boundaries, where lie the boundaries? The first boundary here is lambda over 2 pi. So this is the maximum range. At this range, the reactive near field becomes equal to the far field, and afterwards we only have a radiative field here, no longer reactive field here. Reactive field is much stronger, very close to transmitter, and here is where our bank card works. Bank cards use magnetic field, so H is very large here. In the radiative near field, we have something in between. So E over H, electric field over magnetic field, is close to, but not identical to, the impedance of free space. And the final region, it's defined by the Rayleigh distance. So Rayleigh distance is defined by the size of our radiation source. As long as we are far away, this r is larger than 2d squared over lambda. The Rayleigh distance is the boundary between the Fresnel and the Fraunhofer region. Even this Rayleigh region, we shall see this further on in the lectures. This definition may take different forms here. So this radiative near field is probably the least explored option. Far-field optics is for real radio communication nowadays, long-distance real communication. Reactive near field is for some particular applications when we want to limit our range of our communication, like the bank card or like some RFID tags here. The in-between region, this is where we are trying to make use of the very high spectral efficiencies, like massive MIMO, like communications in the millimeter wave range when with small distance and relatively small antennas, d squared, but much smaller lambda, we can further increment this region. So maybe at 100 gigahertz and 1 meter antenna, this distance is about 1 kilometer, where we can make actual use of this radiative near field to improve our spectrum efficiency. So the story is not as simple as on the picture here, and we should have a more detailed look at the further lectures of what is happening here. Finally, our atmosphere is not transparent. It's not transparent at all frequencies. We have many different resonances of air. So we have molecular absorption in the terahertz region. We have electron resonances, molecular resonances in the terahertz region. We have electron resonances in the ultraviolet region. We also have scattering. Rayleigh scatterings also take place in the atmosphere. Rayleigh scattering, we see is a clear sky, has a blue color. So blue color scatters on the molecules of air to have this Rayleigh scattering. We have windows. Frequencies below 100 gigahertz are pretty, except for some special regions that like the oxygen molecule resonance, the water vapor molecule resonance. We have here mostly good transmission here, so this region is called radio, and in fact the region from 9 kilohertz to 400 gigahertz is reserved for radio communications. Here we need a license to operate our transmitter. On the other end of the one, we still have some windows where we could communicate even through our atmosphere, like the thermal infrared window and the visible window. Visible visible and near infrared. I should also say near infrared here, not just visible window. So we can have some free space communication even this window. We cannot have any almost any free space communications here. Here the free space communication is limited to 10 meters, maybe 100 meters at the lowest attenuation points. Here we may have more than 1000 dB per kilometer, so this is 1 dB per meter distance, 100 dB per 100 meters, so this is excessive. This graph is written as zenith opacity here. Zenith opacity here. Not zenith opacity, but zenith transmission. How much radiation for vertical incidence reaches the free space from Earth, or from space the free Earth, at normal incidence. Yes, we also have a technology issue here. There is very little technology available here. Here we have lasers. We have the very efficient CO2 laser even in the thermal infrared window. We have photodiodes, we have photomultipliers, we have light emitting diodes, we have many different sources and detectors here. Here we have the many different electronic components, the many different transistors that we can use for signal processing here. We have a lack of components, a lack of active devices here, although there are millimeter wave lasers. There are detectors. Some transistors can go nowadays up to 1 terahertz, 3 terahertz. We have some. We still have Schottky diodes that can rectify 3 terahertz, but these components have very bad performance. Very difficult to use. Some thermal infrared detectors have to be cooled to cryogenic temperatures. That's again not something very practical. So it's not practical to be anywhere in between here. Maybe visible windows useful for communication. Thermal infrared uses requires cooled infrared detectors, and radio region down here can work with standard electronics. This is what if we have available. Scattering for the blue sky. That's the reason why I wrote here scattering. So scattering on a blue background. Remember the blue sky here. We go to our final picture for today and make a link comparison. What can we do with today's technology in the Earth's atmosphere, not on Mars, not in the deep space, to our deep space probes. So we both have on this graph, we have this red and purple lines are for wired, for cable communication, and these green and cyan wires are for free space communications. We may have both cable communications over in the radio range, over coaxial cable, in an optical fiber. We can also have both free space communication in the radio range. We can have free space in the optical range. We may also need communications over shorter distances with very high over shorter distances with very high data rates, and we may also need communications, not guided communications, but there is no free space. We have obstacles, we have diffraction loss of the obstacles. So what are our typical examples here, just to mention them? Coaxial cable requires a repeater station around 1 kilometers, maybe 2 kilometers, maybe 500 meters to 2 kilometers, thinking from cable TV, just amplifiers, to digital communication that may have regenerators and may have a longer reach. Coaxial cable is limited between 500 meters and 2 kilometers here. Only 100 megahertz bandwidth, that translates into 140 bits per second over coaxial cable. There were some coaxial cables for 4 times this speed, 560 megabit per second, but they were very rare occasions because of the short range. Fiber has a much wider bandwidth. So transoceanic optical fiber may have a repeater installed in an underwater repeater every 50 kilometers at 10 dB attenuation. And in this way we reach the other end of the ocean. Of course, across the ocean we need to cross 5,000 kilometers. We need on this line around 100 amplifying stations for the optical fiber, where we span 550 kilometers, which each span here of this link. According to the bandwidth, we have about 4 terahertz of bandwidth. In this 4 terahertz of bandwidth, this is related to the minimum attenuation here. This 4 terahertz of bandwidth translates into about 10 terabits per second of capacity. So very high capacity for this link. Nowadays they are using more. They are using also 20 terabits. Very complex modulation schemes to overcome the many other limitations of the optical fiber. You see that all guided communications, the signal decays very quickly, the attenuation grows very quickly with the rising range. So at 1000 kilometers range, we have no communication over over guided lines. If we had those low loss fibers made from special materials like thallium chloride, maybe we could get here, but not with silica fibers. With silica fibers, we end here. Maybe for an we have repeaterless links up to 300 kilometers. 300 kilometers here, where we don't want to have repeaters, just not to have anything under water. We have to reach an island 300 kilometers from shore. We can still do it without repeaters with an optical fiber. But definitely guided waveguides are not suitable for very long communications. Forget deep space here. Deep space, only radio communication and laser communication can go into deep space. So mobile communications also use unguided waves, but these unguided waves at much shorter distances because of the high diffraction loss. So mobile communications do not break records for range nor capacity. Capacity and range, everything is limited here because of the high attenuation. Backplanes at short distances, we may use all of this solution. Even coaxial cable, not coaxial, really twin-ax cable, is used for high capacity backplanes. So this is inside the computer center between different units in a rack or between different racks. Backplanes may use even coaxial or twin-ax cable or optical fiber. Everything is useful here in the backplanes. To have a logarithmic scale here, I had to make such a strange scale. Attenuation in the B +1, so that I can have 1 here, up here. I can have 1. I can have 1 here. Okay, this is for the link comparison. For very long distance, we may have radio communication. The best example today is the Starlink space internet. The distance between the user and the satellite may get, with the satellite low on the sky, satellites are 500 kilometers high here, but you may get to 1000 kilometers or even 2000 kilometers when the satellite is low on the sky at millimeter waves with directional antennas on both sides of the links, electronically steerable directional antennas for Starlink. For even longer distances, the best solution is not radio. The best solution in deep space is actually laser. We may have laser links for intersatellite links in Earth's orbit here. For longer distances, we may use larger mirrors to have millions of kilometers here. And you see that this line does not decay that fast. So we can reach very deep space using laser communications, not radio but laser, making the advantage that laser mirrors have a much higher, transmit much narrower beams than radio antennas. Intersatellite links are also used in the Starlink project, but not for communication through the Earth atmosphere, not for communication to ground, but for intersatellite links in the vacuum of free space. So this is a brief conclusion of description of all possible links we can make. Next time, in the next lecture, we shall see the limitations of the various links. We can only design our electronics once we understand the limitation of a certain link, and we should spend two or three lectures just to see the limitations, what our electronics actually needs to do here, what kind of electronics we need to make all these things happen, to make all these things reality. That's all for today.